Right now, there is a planet 38 million miles away that once had oceans, a breathable atmosphere, and a surface temperature where liquid water flowed freely for over 2 billion years, and in less than 1,000 years, something turned it into the most violent, hostile hellscape in the entire solar system. That planet is Venus. And the terrifying part? Scientists now believe Earth is next. We are going to show you the exact sequence of events that killed Venus, frame by frame. We'll reveal why NASA's latest data is reshaping everything we thought we knew about planetary death. And we'll answer the question nobody wants to ask: are we already watching Earth's future unfold right now? But here's what no one tells you: the 1,000-year window didn't start millions of years ago. Some researchers believe it may have already begun. And I know, when I first read this, my immediate reaction was, that sounds like clickbait. So let me show you exactly where this number comes from, because the data is, honestly, more disturbing than the headline. Let's start with something that I think most people genuinely don't appreciate. Venus and Earth are not just vaguely similar. They are, in the scientific meaning of the word, twins. Both planets formed from the same solar nebula, the same cloud of gas and dust that collapsed roughly 4.5 billion years ago to create our solar system. They sit relatively close to each other in cosmic terms, separated by about 38 million miles at their nearest approach. Venus has a mass equal to 81.5% of Earth's. Its radius is 95% of Earth's. Its density is 5.24 grams per cubic centimeter, compared to Earth's 5.51, a difference of less than 5%. In geology, in chemistry, in their fundamental building blocks, these two worlds are as close to identical as two planets in the same system ever get. For most of the 20th century, Venus was actually placed by astronomers at the inner edge of our Sun's habitable zone, not comfortably outside it. The thinking was, Venus receives more solar radiation than Earth, yes, but maybe, just maybe, conditions could work. And then we sent probes there and found 465 degrees Celsius and atmospheric pressure equivalent to being 900 meters underwater, and everybody quietly updated their assumptions and moved on. But the story didn't end there. Because in 2019, a team at NASA's Goddard Institute for Space Studies, led by climate scientist Michael Way, ran something extraordinary. They took everything we now know about Venus, its rotation rate, its geological structure, its atmospheric chemistry, and they asked a different question. Not, what is Venus like now? But, what could Venus have been like before? They built a supercomputer climate model of an ancient Venus with liquid oceans and lower CO2 concentrations, and they let it run. The results stopped people in their tracks. Under those modeled conditions, Venus's surface averaged around 15 degrees Celsius. Roughly London in summer. Stable. Temperate. Potentially habitable for somewhere between 2 and 3 billion years. To put that in perspective, Homo sapiens has existed for approximately 300,000 years. Venus may have had stable, Earth-like surface conditions for a period 10,000 times longer than our entire species has been alive. I want you to sit with that number for a moment, because I think we have a habit of glossing over it. There's a funny footnote to this whole story, and it involves the fact that for much of the 20th century, science fiction writers were way more optimistic about Venus than the actual scientists. H.G. Wells, Isaac Asimov, countless others, they wrote Venus as a jungle world, lush and dripping, possibly teeming with life. Dinosaurs even. There was a whole genre of Venus adventure fiction built on the assumption that our nearest neighbor was a paradise just waiting to be explored. The irony is that they may have been directionally correct, just off by a few 100 million years. We have spent decades framing Venus as the failed sister of Earth. That framing is wrong. Venus didn't fail. Venus was killed. And the trigger wasn't a meteor. It wasn't a collision with another body. It was something Venus did entirely to itself, and it happened faster than any extinction event in Earth's history. Before we get to the mechanism of death, we need to spend some time with the Venus that existed before. Because I think the loss is only real if you understand what was lost. The most powerful evidence that Venus once had liquid water isn't a photograph or a rock sample. It's a ratio. Specifically, the ratio of deuterium to hydrogen, what scientists call the D/H ratio, in Venus's current atmosphere. Deuterium is a heavier isotope of hydrogen. When water evaporates and escapes into space, the lighter molecules, regular H2O, leave first. The heavier deuterium-laden molecules lag behind, becoming progressively more concentrated in whatever atmosphere remains. Venus's D/H ratio is approximately 150 times higher than Earth's. 150 times. That is an enormous chemical fingerprint. It tells us, with near certainty, that Venus once possessed a massive reservoir of water, and that water subsequently escaped. The scale of the ratio points to oceans, not puddles. Not temporary surface moisture. Oceans. The 2019 Wei et al. Climate model adds another layer. One of the things that makes Venus's ancient habitability plausible, and this surprised me when I first encountered it, is its rotation rate. Venus rotates extraordinarily slowly. One Venusian day lasts 243 Earth days, which is actually longer than Venus's year of 225 Earth days. This seems like it should be catastrophic for surface conditions, with one side baking in continuous sunlight and the other freezing in darkness. But the models suggest the opposite. Venus's slow rotation, combined with an ancient ocean, would have generated a thick cloud layer on the sun-facing side, a natural sunshade that reflected incoming solar radiation back into space before it could heat the surface. Venus's strange rotation, which we tend to think of as one of its alien characteristics, may once have been its primary protective mechanism. When I went through these modeling papers, and I'll be honest, I spent about 3 weeks going through them for this video, there was one image that made me stop. It was a simulated topographic map of ancient Venus with projected ocean coverage overlaid on the terrain. And you're not looking at an alien landscape. You're looking at a world. Coastlines. Continental shelves. The suggestion of river deltas flowing down from highland regions into shallow inland seas. It looks disturbingly like a map of somewhere real. That world may have had its own Cambrian explosion, its own deep ocean trenches, its own versions of the ancient mountain ranges that now sit fossilized in Earth's crust. A world that had a genuine shot at becoming what Earth became, and with 2 billion years of runway, potentially more. But paradise didn't last. And what ended it was not gradual. Scientists now have evidence suggesting the transformation happened in a geological blink, a window so narrow it's almost difficult to accept. How narrow? We'll get to that exact number. But first we need to understand the weapon Venus turned on itself. And here's the part that should catch your attention: it's a weapon that Earth is currently building right now, under our feet. The runaway greenhouse effect sounds like a term from a climate change pamphlet. But as a physical process, it's something much more specific and much more final. Let me walk you through exactly what happens, because the mechanism is as elegant as it is horrifying. Step 1: the sun gets brighter. This is not a theory. It's standard stellar physics. Our Sun increases in luminosity by roughly 10% every billion years as it burns through its hydrogen fuel. For most of Venus's history, this was manageable. The planet's ancient climate system absorbed the slowly increasing energy and maintained equilibrium. Step 2. Slightly warmer temperatures drive more ocean evaporation. More water vapor enters the atmosphere. This seems harmless until you realize that water vapor is itself a greenhouse gas, and for shortwave infrared radiation, it's more potent than CO2. More water vapor traps more heat. More heat drives more evaporation. More evaporation adds more water vapor. This is a positive feedback loop with no natural break built into the system. Step 3. Once ocean surface temperatures reach roughly 70 to 80 degrees Celsius, the evaporation rate exceeds the atmosphere's capacity to cycle water back as rain. The oceans begin a one-way journey upward. At this point, the process is self-sustaining. You don't need additional solar input to keep it going. The planet's own atmosphere is now doing the work. Step 4. Ultraviolet radiation in the upper atmosphere begins splitting water vapor molecules. The lightweight hydrogen atoms escape into space. The oxygen bonds with surface rocks. And the water, all of it, every ocean, every river, every cloud, is gone. Permanently. It doesn't come back because the hydrogen that would be needed to reconstitute it has escaped the planet's gravitational field. What's left is Venus as we find it today, 465 degrees Celsius on the surface, an atmosphere 96.5% carbon dioxide, atmospheric pressure 92 times that of Earth. The CO2 wasn't the cause, it was the consequence. Once the oceans were gone, there was no mechanism left to absorb CO2 from ongoing volcanic outgassing. It simply accumulated. For hundreds of millions of years, it accumulated. The precise theoretical threshold at which ocean loss becomes irreversible has a name, the Komaybayashi-Ingersoll limit. Cross that line, and no amount of time or luck brings the water back. Venus crossed it. And here's the number that I want you to hold on to. By some calculations, Earth currently sits at approximately 80% of this threshold. That figure is contested, I want to be clear about that. Different models give different numbers. But the direction of that number, and what it means given Venus's example, is why planetary scientists keep returning to Venus in their papers about Earth. Carl Sagan, of all people, first proposed the runaway greenhouse effect as an explanation for Venus's conditions back in 1960. The scientific community, at the time, largely dismissed it as too dramatic, too science-fictional. Sagan was right. And many of the scientists who were skeptical of him later contributed to the very models that proved his hypothesis correct. There's a lesson in that about what the most important scientific ideas tend to sound like when you first encounter them. Earth currently has atmospheric CO2 concentrations of around 420 parts per million. The estimated CO2 level on Venus at the moment its tipping cascade began is somewhere between 1,000 and 2,000 parts per million, depending on the model. Earth is currently adding approximately 3 parts per million per year. These are not political numbers. They are planetary physics numbers. Venus does not care about policy debates. The transition is now set up. We know the mechanism. We understand the chemistry. But the question that genuinely disturbed the planetary science community, the question at the center of this video, is about speed. In 2023, a team of researchers published findings that sent shockwaves through planetary science. They weren't arguing about timescales of millions of years. They were arguing about something they called geological punctuation. And the timescale they were working with was measured not in millions of years, but in hundreds. Where does the less than 1,000 years figure actually come from? This is the core of the story, and I want to be precise, because this is the part that gets the most scrutiny, and deserves it. There are three converging research threads. The first comes from Venus's volcanic history. NASA's Magellan spacecraft spent 4 years radar mapping Venus's surface through its opaque cloud cover. What it revealed was a planet that had undergone what geologists call global volcanic resurfacing, essentially, the entire crust replaced by lava flows, approximately 300 to 500 million years ago. This was not localized volcanism. This was planetary-scale volcanic activity that overprinted virtually every surface feature that existed before it. Some models suggest this resurfacing event, which generated catastrophic amounts of CO2 and sulfur dioxide, may have unfolded over less than 1 million years, and possibly, at its peak intensity, far shorter. The second thread comes from pre-mission analysis papers for NASA's DAVINCI mission. Atmospheric layering models designed to predict what Da Vinci's instruments would encounter suggest that once the Komabayashi-Ingersoll limit is breached and the cascade begins, the final completion of ocean loss, under Venus's specific rotation rate and atmospheric circulation dynamics, could take as little as 500 to 2,000 years. The 1,000-year figure is the midpoint of that range. The third thread draws from climate tipping point research more broadly. Work by James Hansen and others, and separately by Wei and Del Genio in their 2020 Venus modeling paper, suggests that once the feedback loop crosses its threshold, the progression to total water loss is rapid on geological timescales. In absolute terms, that means hundreds to low thousands of years. Now here's the epistemic honesty moment, because I think it matters. The 1,000 years figure is not in a single peer-reviewed consensus paper with that precise number. It is derived from multiple research threads, modeling outputs, and the logical endpoint of cascade calculations. Some scientists would argue the transformation took far longer, perhaps 10,000 years, perhaps 100,000. But here's what I'd ask you to consider: even if the transformation took 100,000 years, that is still shorter than the time elapsed since the last ice age maximum. In planetary terms, this was instantaneous. A snap of geological fingers. What does 1,000 years of planetary death actually look like, sequentially? Let me walk you through it, because I think the abstraction of geological timescales obscures how viscerally fast this is. By year 1, average surface temperature has risen 5 degrees Celsius globally. Unusual. Unprecedented by natural standards. But survivable for surface life. By year 50, oceans begin systematic evaporation beyond the recovery threshold. Atmospheric water vapor has created what researchers call a super greenhouse condition. Temperatures are now accelerating faster than any model had predicted, because the feedback is feeding itself. By year 200, equatorial surface temperatures exceed 100 degrees Celsius. Whatever life existed on Venus, and we'll address that question directly, would by this point have been retreating to deep ocean trenches, cave systems, high-altitude environments. The surface is no longer viable. By year 500, the oceans are essentially gone. Whatever moisture remains is trapped in an increasingly acidic atmospheric system. Any life that survived this long has, at this point, 0 options remaining. By year 1000, the transformation is complete. The Venus we would find today if we landed a probe. 465 degrees Celsius. Lead melting heat. 92 atmospheres of pressure. The killing is done. I'm going to take a breath here and acknowledge something directly. I realize I've just dropped a sequence of numbers that, taken together, feel like a lot. And when I was putting this section together, I had a choice about how to present it. You can soften the framing, make it more comfortable, or you can present what the data actually says and let people decide what to do with it. I went with the second option. That's the only kind of documentary I know how to make. The disturbing implication for Earth isn't that we're on a 1,000-year timeline. It's that we now have evidence that a planet can go from a stable, habitable paradise to an absolute hellscape within a window that a civilization could theoretically live through and witness. There is no guarantee of a long warning period. Every IPCC revision has moved timelines earlier, not later. Venus is the case study for what too late looks like. The data that supports Venus's transformation didn't come from theoretical models alone. We went there. We sent robots into that furnace. And what they found is one of the most remarkable chapters in the history of space exploration. The Soviet Union launched 29 missions to Venus between 1961 and 1984. Most of them failed. The ones that actually reached the surface survived an average of 23 minutes before being crushed or melted by conditions that make any environment on Earth look gentle by comparison. Venera 7, in 1970, became the first spacecraft in history to survive landing on another planet. It transmitted data for exactly 23 minutes before going silent. In those 23 minutes, it confirmed one number, 475 degrees Celsius at the surface. The scientists at Mission Control went quiet for a long time after receiving that transmission. They'd known theoretically what to expect. Knowing and receiving the data are different things. Venera 9 and 10, in 1975, sent back something even more unexpected, the first photographs from Venus's surface. They were black and white images, slightly blurred, but what they showed was striking. Angular, sharp-edged rocks. Unweathered. On Earth, exposed rocks become rounded over time. Wind, water, thermal cycling all gradually smooth them. On Venus, with its dense, slow-moving lower atmosphere, the rocks had barely eroded. Some of those rocks may have formed millions of years ago and look essentially new. Venera 13, in 1982, added color. The surface of Venus is orange, lit by the diffuse glow that filters through its cloud layers. The rocks photographed by Venera 13 are flat, layered, slate-like. Some planetary geologists have noted they bear a structural resemblance to sedimentary rocks, rocks that form, on Earth, in the sustained presence of liquid water. NASA's Magellan mission, running from 1989 to 1994, used synthetic aperture radar to map 98% of Venus's surface through its impenetrable cloud cover. What it revealed was a landscape of extraordinary violence and complexity, 167 volcanoes larger than 100 kilometers in diameter, more large volcanoes than any other planet in the solar system. Tesserae terranes, which are regions of highly folded, deformed ancient rock that predate the global resurfacing event, the oldest surviving geological features on Venus. And unique structures called pancake domes, circular volcanic formations found nowhere else, possibly formed by viscous lava extruding under atmospheric pressure conditions fundamentally different from today's. In 2023, a fresh analysis of Magellan data by Robert Herrick at the University of Alaska found direct evidence of active volcanic eruption, a vent feature that had visibly changed shape between two radar passes in 1990 and 1992. Venus is not geologically dead. It is still erupting, still releasing CO2, still adding to an atmosphere that already has nowhere to put it. But here's the feature that stays with me. Venus has channel systems, called canali, that stretch for extraordinary distances across its surface. The longest of them, Baltus Vallis, runs 6,800 kilometers. The Nile, the longest river on Earth, is 6,650 kilometers. Baltus Vallis is longer. These channels cannot be water features in Venus's current state. The temperature and pressure make liquid water physically impossible at the surface. The accepted explanation is ancient lava flows, rivers of molten rock that carved channels across the landscape during periods of intense volcanism. But some planetary geologists have noted that the meandering quality of Baltus Vallis, the way it curves and bends in patterns more consistent with fluid erosion than with lava dynamics, is difficult to fully explain by volcanism alone. A minority hypothesis, peer-reviewed but far from consensus, suggests some channel features may have originated when Venus had liquid water and were subsequently preserved or modified by later volcanic activity. If that hypothesis is correct, Baltus Vallis is a fossilized river, longer than the Nile, cut into the surface of a world that has been burning for hundreds of millions of years. Think about the Soviet engineers who built Venera 7. They knew it was going to be destroyed. They designed a spacecraft specifically to survive as long as possible in conditions that would obliterate it, and they gave it 23 minutes. In those 23 minutes, it changed our understanding of the solar system. There's something almost painfully human in that, building something carefully, knowing it will die quickly, and learning everything you can in the time it has left. The probes gave us data. The data gave us questions. And the biggest question, the one that keeps planetary scientists working late, concerns timing. Specifically, whether what happened to Venus could have happened at a moment when there was something on Venus worth destroying. If Venus had liquid water for 2 billion or more years, and if we accept that life on Earth arose within roughly 500 million years of liquid water becoming available, then Venus had 4 times that window. 4 times as long as it took for life to emerge on Earth. The conditions for life are more flexible than we once assumed. Earth's biosphere has been found thriving in environments that would have seemed impossibly hostile a century ago. Black smoke or hydrothermal vents at 350 degrees Celsius, Antarctic ice at -20 degrees, environments with pH levels near zero. Life, once it exists, is extraordinarily tenacious. The real uncertainty about Venus isn't, could life have started? Given the timeline, the chemistry, the available liquid water, statistically it's almost harder to construct an argument that it couldn't have. The uncertainty is, how far did it get? In September 2020, astronomer Jane Greaves of Cardiff University announced the detection of phosphine, pH 3, in Venus's upper atmosphere. Phosphine is notable because it has no known abiotic production route at the concentrations detected. On Earth, phosphine is produced almost exclusively by biological processes, specifically by anaerobic microorganisms. Its presence in Venus's clouds triggered a scientific debate that is still ongoing. The original detection paper was challenged, reanalyzed, partially revised, and partially confirmed. The current status of the phosphine question is, the signal is real, the interpretation is contested, and there is a residual unexplained component that known abiotic chemistry cannot fully account for. If phosphine is present at meaningful concentrations, the most viable explanation involves an aerial biosphere, microbial life living in Venus's cloud layers at an altitude of around 50 kilometers, where temperature and pressure are surprisingly Earth-like, roughly 50 degrees Celsius, approximately 1 atmosphere of pressure. These clouds would be the only survivable environment remaining, if life had somehow migrated upward from the surface before or during the catastrophe and adapted over subsequent millions of years to the acidic conditions. I want to be honest with you about how I've wrestled with presenting the phosphine story here. Science journalism has a habit of sensationalizing the announcement and then sensationalizing the debunking, and the viewer ends up with whiplash rather than understanding. My honest read is this: the signal is real, the interpretation is uncertain, and the uncertainty is itself the most interesting part. We don't yet know. That's the truth. What we do know is that if life existed on Venus when the catastrophe struck, even purely microbial life, it had no warning and no response. The surface transformation, happening within centuries to millennia, would have outpaced any biological adaptation. And the geological violence that followed, the global volcanic resurfacing, the cumulative heat, the acid rain, would have destroyed the surface record completely. Any fossil evidence that once existed has been remelted multiple times over. Venus has erased its own history. This is the deepest tragedy in the story, not just that a world died, but that it may have taken a permanent record of itself down with it. The Fermi paradox asks why, in a universe this vast and this old, we see no signs of other civilizations. One answer, the Great Filter Hypothesis, suggests there is a nearly insurmountable bottleneck somewhere on the path from simple chemistry to spacefaring civilization. Venus may be the closest evidence we have for where one version of that filter might be located, not in the rarity of life's origin, but in the physical processes that can end a biosphere faster than any civilization can respond to it. The filter might not be a cosmic war or a gamma-ray burst. It might be a planet doing exactly what Venus did, quietly, rapidly, and with geological finality. Whether or not life existed on Venus, the catastrophe forces a rethinking of rules we thought we understood. And the planet that keeps appearing in comparison, paper after paper, is Earth. Earth has something Venus apparently lost, or possibly never fully had: active plate tectonics. Earth's tectonic system is, among other things, a planetary thermostat. Carbon gets absorbed into marine sediments, subducted into the mantle through plate boundaries, and eventually released as CO2 through volcanic activity. That CO2 gets absorbed by weathering of surface rocks, washed into the ocean, and the cycle repeats. This is the carbon silicate cycle, and it has maintained Earth's surface temperature within a relatively narrow range for approximately 4 billion years. It is, in a very real sense, what has kept Earth from becoming Venus. Venus appears to have stopped this cycle. The most likely reason is circular and brutal. It may have lost its water, which is what lubricates tectonic plate movement, and without water, the tectonic system ceased. Without tectonics, the carbon silicate cycle stopped. Without the carbon silicate cycle, CO2 from volcanic activity had nowhere to go except up, and up, and up. The thermostat broke, and the temperature climbed to where it is today. The troubling question is whether Earth's tectonic activity is permanent. It's not. Some geophysical models suggest Earth's tectonic system could begin slowing within 1 to 2 billion years as the interior cools. Other, more controversial models raise the possibility of disruption on shorter timescales under specific conditions. The billion-year figure seems safely distant until you consider that the current trajectory of atmospheric CO2 is compressing effective timescales in ways that are only beginning to be modeled. Dewey et al. 2019 paper did something else important beyond confirming ancient Venus habitability. It forced a revision of how we calculate habitable zones for planets elsewhere. For decades, NASA's habitable zone calculations placed Venus clearly outside the optimistic inner boundary. The 2019 work pushed that boundary inward, meaning the habitable zone is wider than we thought. That's ostensibly good news for finding life elsewhere. But the accompanying lesson is sobering: being inside the habitable zone does not guarantee survival. A planet can have everything it needs and still lose it all. The zone defines opportunity. What happens within it depends on processes that can cascade beyond recovery. On Earth, right now, 3 specific dynamics carry a recognizably Venusian signature. Methane hydrates in Arctic permafrost are destabilizing as temperatures rise. Methane is roughly 25 times more potent as a greenhouse gas than CO2 over a 20-year period. If permafrost thaw releases methane at sufficient scale, it triggers the same positive feedback structure that drove Venus's cascade: warming begetting release begetting warming. The West Antarctic ice sheet contains enough frozen water that its destabilization would raise global sea levels by 3 to 5 meters. Current models suggest the tipping point for WACE may fall within 2 degrees Celsius of warming, a threshold Earth is currently approaching. Ocean acidification is proceeding at a rate faster than at any point in the last 300 million years, including during the Permian extinction event. The oceans are Earth's primary carbon buffer. If they saturate and can no longer absorb atmospheric CO2 at current rates, the carbon silicate cycle loses a critical component. None of these individually mean Earth is becoming Venus. But each represents a data point in a direction. And Venus is what the destination of that direction looks like. I realize this section is heavy. I've been told before that this kind of documentary makes people feel hopeless, which is genuinely the opposite of what I'm going for. So let me be direct, I'm not showing you Venus to produce despair. I'm showing you Venus because it is the most important data point we currently have about what planetary death looks like from the outside. And you cannot use data you haven't been given. There is one absolutely critical difference between Venus and Earth, and it matters more than any of the similarities. Venus had no one to notice what was happening. It had no civilization building climate models, no scientists reconstructing the mechanism of its own planet's death, no probes being designed to recover its atmospheric record. It died without a witness. We are the witness. For the first time in the history of this solar system, there is a species capable of looking at a dead planet, understanding how it died, and recognizing the relevance to its own situation. That capability is not nothing. That is, in fact, extraordinary. For the first time in 30 years, we are going back to Venus. Not with one mission, with 3. DAVINCI launches in the late 2020s to early 2030s. Its full name, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, describes exactly what it's designed to do. The probe will descend through Venus's entire atmosphere in a roughly 63-minute freefall, taking continuous measurements at every altitude from the cloud tops to the surface. The key measurements are noble gas ratios, argon, neon, xenon. Noble gases are chemically inert. They don't react with surface rocks or atmospheric compounds. They survive planetary transformations essentially unchanged. By measuring Venus's noble gas abundances with precision, scientists can determine whether Venus formed with a chemical composition similar to Earth's, supporting or challenging the twin hypothesis, and can estimate the volume of water Venus originally possessed. The noble gases are, in a sense, Venus's birth certificate, preserved in an atmosphere that has otherwise been transformed beyond recognition. DAVINCI also carries a camera designed to image the Tesserae highlands, those ancient terrain regions that survived the global volcanic resurfacing. If those highlands show ancient shorelines, sedimentary mineral layering, or chemical compositions consistent with formation in the presence of water, it will constitute direct physical evidence of ancient Venusian oceans. DAVINCI is a time capsule reader, designed to extract a planetary origin story that Venus has been concealing for hundreds of millions of years. VERITAS, Venus emissivity, radio science, NSAR, topography, and spectroscopy, will create a surface map with resolution approximately 100 times greater than Magellan's. 30 years of instrument development makes this possible. VERITAS is designed to identify active volcanic zones, measure heat flow from the interior, and determine whether Venus ever had plate tectonics. Its NSAR capability can detect ground deformation at centimeter scale over time, potentially catching Venus's geology in motion for the first time, in real time. ESA's Envision mission, targeting launch around 2031 to 2032, focuses on atmospheric chemistry. Its instruments are specifically designed to settle the phosphine question definitively. In roughly 10 to 15 years, we will know whether something is living in those clouds. One way or another, we will know. The fact that all 3 missions are happening within the same decade is not coincidence. The 2021 Planetary Science and Astrobiology Decadal Survey, the document that sets NASA and the broader planetary science community's research priorities for a decade, ranked Venus missions at the top of its recommendations, describing Venus as a Rosetta Stone for understanding planetary habitability. That phrase, in an official scientific strategy document, is not casual language. It means, this is the key to understanding everything else. I want to be honest here, I am not a planetary scientist. I'm someone who has spent an embarrassing amount of time reading papers by planetary scientists and trying to translate them accurately. If I've gotten something wrong in this video, I want to hear about it. That's not a legal disclaimer. That's a genuine invitation, because getting this right matters more than protecting my credibility. When DAVINCI delivers its data in the early 2030s, you will be one of the people in the world who actually understands what it's looking for and why it matters. Most people will see the headline. You'll understand the story behind the headline. And what confirmation would mean, the stakes if these missions return the answers most planetary scientists privately expect, is worth being clear about. If DAVINCI confirms ancient Venusian oceans, Venus becomes the first confirmed case of a habitable planet dying. Every habitable zone calculation gets revised. Every exoplanet survey gets reoriented. The implications for astrobiology, for climate science, for how we think about existential risk are enormous. If Envision confirms a biological phosphine signature, we will have found the first evidence of extraterrestrial life, not on a distant exoplanet we can barely resolve, but on our nearest neighbor. The planet visible with the naked eye in the evening sky, that humans have been observing for millennia without knowing what it was hiding. These missions are not just about Venus. They are about whether the universe is full of dead versions of what we could have been, and whether we are on a trajectory to join them. We've been through a lot of data. I want to step back from the scientific architecture for a moment and ask the question that doesn't appear in any of the research papers, the question that I think is the most important thing Venus's story actually raises. Venus is the first example in human history of a world we have genuine scientific reason to believe was habitable, and is now dead. Not speculatively habitable. Not could be habitable. Habitable by the chemical evidence of its own preserved atmosphere. Measurably, verifiably, isotopically habitable. This changes the context of Earth's existence in a way that I don't think we've fully absorbed as a culture. Earth is not the default state of a planet in the habitable zone. Earth is one outcome in a range of outcomes, and we have now seen another outcome, 38 million miles away, clearly enough to study it at the molecular level. The Great Filter, Robin Hansen's 1998 framework for thinking about why the universe appears silent despite its age and scale, has 2 possible locations. Either the filter is behind us, the emergence of complex life or consciousness is so improbable that we are essentially alone and have already passed the bottleneck, or the filter is ahead of us, and civilizations consistently fail to achieve permanence for reasons that are physical, environmental, or self-inflicted. Venus is potential evidence for the second option. Not because Venus had a civilization, but because it demonstrates that the physical processes capable of ending a biosphere are not exotic or rare. They are planetary standard equipment. They operated next door to us. They may be operating now, in slower form, on the planet we're standing on. The quiet, burning, nearest neighbor version of the Great Filter might not be an alien war. It might be a world doing exactly what Venus did, crossing a threshold, initiating a cascade, completing a transformation, all without drama and without warning. But here's the counter-argument, and I mean it with full force. What is different about Earth in 2024, compared to Venus at any point in its history, is that we know. We have built the models. We have sent the probes. We have recovered the chemical fingerprints from a dead world's atmosphere and reconstructed the mechanism of its death. We can look at Venus and say, with scientific precision, that is what happens when certain conditions are met, and here is what those conditions look like, and here is how far we currently are from meeting them. No other known civilization in the history of this solar system has ever had that capability. Venus had no Da Vinci mission. It had no researchers reconstructing its atmospheric history 300 million years after the fact. It died quietly, alone, with no one watching and no one learning from it. We are watching. We are learning. And watching, genuinely watching, with the instruments and the models and the willingness to confront what we see, is the first step that was never available before. I've made a lot of space documentaries. Most of them leave me feeling awe, the kind of awe that comes from scale, from distance, from the sheer improbability of existing in a universe this old and this large. This one left me feeling something different. Something closer to urgency. Not panic. Not despair. But the specific feeling you get when you realize that the thing you're looking at is directly relevant to you, personally, in the present, not in the abstract. I don't think that's a bad feeling. I think it might be a necessary one. At the beginning of this documentary, I told you that Venus once had oceans, a breathable atmosphere, and liquid water flowing on its surface. That something killed it in less than 1,000 years. That's still true. But what I want to add now, at the end, Venus also had 2 billion years of relative stability before the killing began. And we are still in ours. Let me bring this home with 3 things I think are the actual takeaways from Venus, not the terrifying version, not the sanitized version, but the true one. Lesson 1, stability is not a permanent state. It's a balance you can tip. Venus had 2 billion years of stable, temperate conditions. Then the balance shifted, slowly at first, then all at once. The scientific concept underlying this is hysteresis, a system's tendency to maintain its current state until a threshold is crossed, after which it rapidly transitions to a new stable state that may be radically different from the previous one. Earth's climate system exhibits hysteresis. So does every complex interconnected system. The practical implication is that stability feels normal from the inside, right up until it doesn't, and the system gives very little warning about which incremental change is the one that crosses the threshold. The Venusians, if they existed, never saw the end coming. The end came from within the same system that had sustained them. Lesson 2, 1,000 years is both an eternity and a geological instant. 1,000 years ago, human civilization had no industry, no fossil fuels, no global communication, no capacity to observe or influence atmospheric chemistry at planetary scale. 1,000 years from now, human civilization will be something we cannot currently imagine, interplanetary, post-scarcity, or absent. The Venus timescale tells us that catastrophic planetary transformation can unfold within a span that a civilization could actually witness, beginning to end, in real time. If Venus's final cascade took 1,000 years, and something analogous began on Earth today, your descendants 9 or 10 generations from now would live through the completion of it. That is not an abstraction. That is the length of time between us and the Norman conquest of England, a span with names and faces and recorded history. Lesson 3, proximity is the most powerful teacher in science. We have cataloged thousands of exoplanets. We have developed models for millions of possible worlds. And yet nothing has taught us more about planetary habitability, its conditions, its fragility, its failure modes, than Venus, 38 million miles away, visible to the naked eye, reachable with rockets we already know how to build. The most important discoveries about life in the universe, about how planets die, about what Earth is and what it isn't, may not require looking to distant stars. They may require us to fully understand the two worlds directly next door, Venus, which shows us what habitability looks like when it fails catastrophically, and Mars, which shows us what it looks like when it fades slowly. Earth is the planet that has, somehow, improbably, avoided both endings. So far. Venus has sent shockwaves through planetary science not because it is a distant mystery but because it is right here, and it tells the darkest chapter of a story that Earth is currently in the middle of writing. The turning point in Earth's history may not be in the past. It may be now. And Venus, silent, burning, 38 million miles away, is the data point that reshapes everything we thought we knew about what normal means for a planet like ours. One last thing. I'm going to go on record. I believe the Venus missions of the 2030s will be among the most consequential scientific missions in human history. More important than the moon landings for what they revealed about our place in the solar system. More important than Voyager for what they'll reveal about how planets live and die. Because they will tell us what happened to our twin. And knowing what happened to your twin, across 38 million miles of space and several hundred million years of silence, is how you give yourself a chance to write a different ending. In this space documentary, we've traveled 2 billion years into Venus's past, walked through the mechanisms of a planetary transformation, examined the possibility that something may once have lived and died there, and arrived at the present moment, where 3 spacecraft are being assembled right now to finally answer the question Venus has been asking us across that 38 million mile gap: what happened to me? And could it happen to you? The answer to the first question is coming. The answer to the second question, we are all writing it together, right now, every day. The next time you see Venus in the evening sky, and it is visible to the naked eye for much of the year, the brightest object after the moon, I hope you see something different than you saw before. I hope you see a 2 billion year civilization that almost was, a warning written in fire, and a reminder that we are the first species in the history of this solar system that can actually read it. If this changed how you see Venus, or Earth, I want to hear about it in the comments. Not just, great video. Tell me what hit you differently. What question are you leaving with? Because the best part of making these documentaries is the moment someone writes, "I never thought about it that way." That's why this exists. The links to the NASA DAVINCI mission page, the Michael Way 2019 Geophysical Research Letters paper, and the Venera program archive are in the description. This topic does not end here. Next time, we're going to Venus's other neighbor. Mars didn't die in fire. Mars died in silence, slowly, over billions of years, in almost the exact opposite way. Mars is the slow death. Venus is the fast death. And Earth is the planet that has somehow, against considerable odds, avoided both. So far. You know what? I want to pause on that last line for a second, because I think it's the thing this entire documentary has been building toward, and it deserves more than just a passing note. So far. 2 words. And they carry the entire weight of everything we've covered in the last hour. We started this journey with a planet that looked, on paper, indistinguishable from the one you're standing on right now. Same size. Same mass. Same distance from a yellow star in the right zone for liquid water. Same raw ingredients from the same primordial cloud of gas and rock. Venus and Earth were born together, and for the first 2 billion years of the solar system's history, they ran in parallel, 2 experiments in habitability, side by side. And then one of them crossed a line that it could not uncross. And now one of them is the brightest object in your evening sky and the deadliest surface in the inner solar system, and the other one is where you're sitting right now, watching a documentary about what went wrong next door. That asymmetry, that gap between what Venus is and what it was, between what it could have been and what it became, is the most important scientific story of the 21st century. Not because Venus is exotic or distant, because it is neither. Here's the thing I kept coming back to while putting this together, and I'll be honest with you the way I try to be honest in every one of these documentaries. I almost didn't frame this video around the 1,000-year collapse window. My instinct was to lead with the habitability story, the ancient oceans, the 2 billion years of stability, the possibility of life, because that's the hopeful version, the wonder-filled version, the version that makes you feel the scale of deep time in a way that's almost spiritual. And I love that version of this story. But the data kept pulling me back to the collapse. Because the data is not subtle. When you look at the Venus Express sulfur dioxide measurements from 2006 through 2014, when you read the Michael Way paleoclimate modeling papers, when you go through the Magellan radar topography results and start asking what the volcanic provinces tell us about heat flow timing, the story that emerges is not primarily about ancient wonder. It's about speed. It's about how fast a planet that was fine can stop being fine. And that part of the story, the speed part, is what I think we owe it to ourselves to sit with. Because speed is the variable that changes everything. If Venus's transition from habitable to Hellscape took 100 million years, it would be a geological curiosity, interesting, but not urgent. If it took 10 million years, it becomes a case study in slow planetary evolution. But if it took 1,000 years, or even 10,000 years, if the cascade from stable to catastrophic happened within a window that an intelligent civilization could observe in real time, then it stops being history and starts being warning. And warnings only work if you receive them before the threshold, not after. Venus cannot tell us that warning anymore directly. Whatever record it once held of its own transformation is buried under 50 kilometers of crushing CO2 atmosphere and half a kilometer of volcanic resurfacing. The surface we mapped with Magellan in the 1990s is geologically young, shockingly young for a planet 4.5 billion years old, which tells us the old surface, the surface that would have shown us the ancient oceans, the impact craters from the early solar system, the geological record of the first billion years, was erased. Rolled over. Buried by the very same volcanic event cascade that ended the habitable era. Venus didn't just die. It destroyed the evidence of its own life. That fact stops me every time I return to it. There is a planet 38 million miles away that may have harbored life for longer than multicellular organisms have existed on Earth, and the record of that life, if it existed, was systematically obliterated by the same process that killed it. We are working with fragmentary evidence, incomplete models, and the geological equivalent of a crime scene that the perpetrator set on fire on the way out. And yet, here is where I want to end, not in despair but in something that I think is more useful, and yet we are not helpless. We are not Venus. Not yet, and not because of some cosmic luck that we have no influence over. We are not Venus because we are the first species in the history of this solar system that developed the capacity to understand what happened to Venus. That is not nothing. That is extraordinary. A planet that evolved intelligence, and that intelligence then looked at the neighboring planet and figured out, from the chemistry of its clouds, from the temperature of its surface, from the dynamics of its atmosphere, from models running on computers that didn't exist 40 years ago, what went wrong there. The universe has no precedent for this, as far as we know. It has never happened before, in any system we've observed. A living planet reading the autopsy of a dead one. The 3 missions heading to Venus in the 2030s, DAVINCI, Envision, and the European Space Agency's companion program, are not just scientific expeditions. They are the first time any civilization has deliberately sent instruments to understand the full story of how a planet like theirs died. We are doing the thing that the Venusians, if they existed, never had the chance to do. We are investigating our own potential future while there is still time for that investigation to matter. That might be the most important sentence in this entire documentary. We are investigating our own potential future while there is still time for that investigation to matter. I don't know what the Da Vinci probe will find when it descends through Venus's atmosphere and hits the surface, and it will hit the surface, because nothing lands softly in 92 atmospheres of pressure at 465 degrees Celsius. I don't know what the radar mapping from Envision will reveal about the geological timeline of Venus's volcanic resurfacing events. I don't know whether the ancient Tessera highlands will show us chemical signatures of sedimentary rock laid down in liquid water, which would be extraordinary, a direct fingerprint of oceans that once existed. I don't know. Nobody knows yet. That's why we're going. But I know this: every answer those missions return will reshape everything we thought we knew about what it takes to keep a planet alive. Every data point will sharpen our models of how Earth's own climate system works, where its thresholds are, how much pressure it can absorb before the hysteresis breaks and the cascade begins. Venus is not just a story about the past. It is the instrument we needed all along to understand our own present, and we are only now, after 50 years of neglect, deciding to use it properly. The next time you see Venus, and go outside tonight if you can, because if it's in the evening sky it is unmistakable, the brightest point of light that isn't the moon, hanging low on the western horizon after sunset. I want you to think about this: that light has been traveling 38 million miles to reach your eyes. It is sunlight, reflected off the thick sulfuric acid cloud deck of a planet that rotates backwards, slower than it orbits, wrapped in an atmosphere that would crush and cook you in under a second. And that same light, 2 billion years ago, was bouncing off the surface of an ocean. Off liquid water. Off a sky that might have been blue, or something close to blue, under a sun that was slightly dimmer and slightly cooler than the sun we know today. That ocean is gone. That sky is gone. The water that once covered Venus is gone, dissociated into hydrogen and oxygen by ultraviolet radiation, the hydrogen escaping to space atom by atom over millions of years, the oxygen absorbed into rock and lost to volcanic outgassing. There is no trace of it left, except in the models, and in the deuterium to hydrogen ratio in Venus's remaining atmospheric water vapor, a chemical ghost of ancient oceans, measurable with spectrometers, telling us through isotope ratios that water was once there in quantities that would have covered the surface to an average depth of several hundred meters. Several hundred meters. A global ocean. On Venus. Gone now. And somehow, across billions of years of silence, the ghost of that ocean is still faintly visible if you know where to look. That's the thing about Venus that stays with me. It keeps leaving evidence of what it once was, even as it erases that evidence, even as the heat and pressure and time work to obliterate everything that came before. The deuterium ratio survives. The highland tessera regions survive, peaking above the volcanic plains, possibly holding the chemical record of ancient geology. The gravity field anomalies survive, telling us about interior dynamics we can barely interpret. Venus is trying to tell us its story. We just have to be willing to listen carefully enough, and send the right instruments to do the listening. We are finally doing that. After 50 years of turning our attention to Mars, which is a wonderful and important target, and we will absolutely be covering Mars next, we are going back to the world that is most like ours, to ask it the question that matters most. What happened to you? And what does it mean for us? Those questions are worth the 38 million miles. They are worth the engineering challenge of building probes that survive for even a few minutes on the most hostile surface in the solar system. They are worth the decades of waiting, the budget battles, the long gap between Magellan in the 1990s and the new wave of missions finally launching in the 2030s. Because the answers will do something no other scientific program can do, they will tell us the full range of what a planet like Earth can become. They will give us the complete data set. And right now, we are making decisions about the future of this planet with an incomplete data set. Venus is the missing half of the picture. So, go look at it tonight. Venus, in the sky, exactly where it has always been, exactly where ancient astronomers watched it and called it the morning star and the evening star and built myths around it and worshipped it and wrote its movements into their calendars. They saw a light and they made stories about it. We see a light and we've been able to read the story it was always trying to tell, a story about oceans and transformation and a catastrophic shift that reshaped an entire world in what may have been, by geological standards, a single terrible moment. We are the first civilization in the known universe to be able to read that story. The least we can do is not ignore the ending. And if after everything, the ancient oceans, the volcanic cascade, the sulfuric clouds, the 92 atmospheres, the backwards rotation, the 465-degree surface, the possibility of life that rose and was buried before we ever had the chance to find it, if after all of that you're still somehow not convinced that Venus is the most interesting object in the solar system, I'll just say this. It's also the brightest thing in the night sky that isn't trying to burn you, which is more than we can say for the Sun, so really, Venus is already winning on multiple metrics. Go outside and find it, that bright, steady, unblinking point of light low on the horizon, and just know that you are looking at the best warning our solar system ever gave us, the one we almost missed entirely, the one we are only now, at what might be exactly the right moment in human history, finally learning to read. And if that doesn't make you want to subscribe to the channel that just made you genuinely emotional about a planet you've never been to and never will visit, then Venus truly has taught us nothing about the consequences of ignoring warning signs right in front of us. Because here is the thing about warning signs, they only work if someone is paying attention. Venus has been hanging in our sky for the entirety of human civilization, the brightest object most people will never think twice about, and for most of that time we looked at it and saw a goddess, a twin, a mirror, and then, when we finally got close enough to see what it actually was, we flinched and turned away toward Mars, toward the outer planets, toward anything that didn't make us feel the particular discomfort of looking at a dead version of ourselves. That discomfort is the point. That is precisely the information Venus has been transmitting for 4.5 billion years, patient and relentless and utterly indifferent to whether we receive it or not. We are receiving it now. The missions are coming. The data is coming. And when it arrives, it will either confirm our worst models or revise them, and honestly, right now, I am not entirely sure which outcome I am hoping for. If the data confirms that Venus crossed its tipping point rapidly, irreversibly, in a geological eye blink, that is terrifying, but at least it is clear. It tells us the threshold is real, that once certain feedback loops engage, the game is over, and that the margin for error on a planet like Earth is not centuries but possibly decades. If the data surprises us, if it shows that Venus's transformation was slower and stranger and more complex than our current models suggest, that is also terrifying in its own way, because it means we understand planetary death even less than we thought, and we are navigating Earth's climate future with instruments we do not yet know how to read. Either way, Venus wins the argument. Either way, it turns out the brightest light in the evening sky was never a star, it was always a question, waiting for a civilization smart enough and honest enough to finally answer it. Go find it tonight. That unblinking point of light, that chemical ghost of ancient oceans, that 4.5 billion year warning written in sulfuric acid and deuterium ratios and backwards rotation, it has been there the whole time. And now you know exactly what it means. If Venus doesn't haunt your evening walks for the next few weeks, we clearly haven't been spending enough time together, so come back soon, because next time we're going somewhere that will make Venus look positively cozy by comparison. Right now, somewhere in a NASA facility, an engineer is stress testing a titanium probe casing designed to survive a surface pressure equivalent to being half a kilometer underwater, in temperatures hot enough to melt lead, surrounded by clouds of concentrated sulfuric acid, and that engineer goes home at the end of the day, looks up at the brightest point in the evening sky, and thinks, "We are going back." That is where we are. That is the moment we are in. And everything we covered in this journey, the ancient oceans that may have persisted for 2 billion years, the deuterium fingerprint that betrayed their existence, the volcanic cascade that may have triggered the end in less than 1,000 years, the Soviet probes that lasted minutes on a surface that should be physically impossible to land on, the phosphine controversy that split the scientific community down the middle, the Tessera highlands that may be holding billion-year-old geological secrets above the lava plains, all of it is about to get an answer. Not a theory. Not a model. An answer. DAVINCI Plus will drop through that atmosphere and spend 62 minutes reading it like a book, layer by layer, measuring the noble gas ratios and isotopic signatures that will tell us, definitively, whether Venus ever had oceans or whether the deuterium signal has been misleading us all along. VERITAS will map the surface at a resolution that makes Magellan's radar imaging look like a sketch drawn from memory. Envision will study the interior dynamics, the volcanic activity, the gravity anomalies, building a picture of what is happening inside Venus right now, not just what happened on its surface billions of years ago. And when those results come back, the conversation about planetary climate tipping points will never be the same. Because right now, the entire framework for understanding how a planet transitions from habitable to uninhabitable is built on a sample size of 1, Earth, trending in one direction, with no completed example of what the destination looks like. Venus completes the picture. Venus is the case study we have been missing, the controlled experiment that the solar system ran on our behalf before we existed to observe it. I want to slow down here for a moment, because I think there is something worth sitting with before we close out. We have spent this entire journey treating Venus as a warning, as a cautionary tale, as the ghost of Earth's possible future. And that framing is accurate and important. But I think it undersells something. Venus is also a record of survival. Not planetary survival. Venus, as a biosphere, did not survive. But the record itself survived. The evidence survived. Against every reasonable expectation, across 4.5 billion years of geological violence and atmospheric transformation in surface temperatures that should have erased everything, enough of the story remained legible for a civilization on the neighboring planet to eventually read it. The deuterium ratio survived. The highland terrain survived. The gravity field survived. The chemical signature survived. That is not nothing. That is, in fact, extraordinary. It means the universe keeps receipts. It means that even the most catastrophic planetary transformations leave traces, and that those traces, if you send the right instruments and ask the right questions, will tell you what happened. There is something almost, I want to be careful with this word, but almost generous about that. The cosmos does not hide the evidence. It just requires that you care enough to look. We are looking. After decades of looking away, of finding Mars more comfortable to study because its story is less personal, we are turning back toward the twin that diverged, and we are going to read its story from beginning to end. And whatever that story says, it will make us better stewards of the only other planet in the solar system confirmed to have pulled off the extraordinary trick of remaining habitable long enough for intelligence to emerge. That trick is rarer than we used to think. That is perhaps the deepest lesson Venus has to offer, not the terror of the runaway greenhouse, not the sulfuric acid clouds, not the surface pressure or the backward spin or the 900-degree days, but the quiet statistical reality that a planet that starts in the habitable zone, with liquid water and a thick atmosphere and the right mass, can still end up as a monument to what used to be there. The habitable zone is not a guarantee. It is an opportunity. And opportunities, as Venus demonstrates with every orbit, can be lost. So here is what I want you to carry with you after this. Not anxiety, there is enough of that already, and Venus is not a reason to despair, it is a reason to pay attention. Not detachment either, that comfortable intellectual distance where we treat planetary catastrophe as an interesting data point rather than something with stakes. What I want you to carry is the specific quality of attention that Venus demands, the willingness to look at something uncomfortable and keep looking, to follow the evidence past the point where it stops being reassuring, and to take seriously what the data is actually saying rather than what we would prefer it to say. That quality of attention is what the next decade of Venus science requires. It is also, not coincidentally, exactly what the next decade of Earth science requires. Those two things are not separate. The same intellectual courage that allows us to look at Venus and say, yes, this is what a runaway greenhouse looks like, this is what the endpoint of unchecked feedback loops produces, that same courage is what allows us to look at our own atmospheric data and update our models honestly, even when the updates are uncomfortable, even when the revised timelines feel too fast to be real. Venus felt too fast to be real too, if our current best estimates are correct. And yet there it is, 38 million miles away on average, the brightest light in the evening sky that isn't a star, patient and indifferent and absolutely certain of what it has to teach us, if we are willing to be the kind of civilization that learns from what the solar system is showing us rather than the kind that looks up, admires the brightness, and goes back inside. We are finally becoming the kind that looks closer. The missions are proof of that. And what we find there, in the clouds, on the surface, in the ancient highlands, in the isotopic ratios of a ghost ocean that evaporated before the first complex life arose on Earth, what we find there will reshape everything we thought we knew about what it means to live on a planet, what it takes to keep one alive, and how thin, genuinely, the line is between the world we have and the world that Venus became. Go outside tonight and find that bright, steady point of light. And hold both things at once, the beauty of it and the warning in it, because that tension, that refusal to look away from what Venus is actually telling us, is exactly the kind of attention that a planet with a future requires from the civilization lucky enough to still have one.